Well, now having it discussed about the various examples of systems such as processing of the continuous time signal using a discrete time system and also processing of a discrete time system using a continuous time signals and also the basic example of a feedback control system. So any system which can be defined as a entity which is normally going to give a response based on the given input signal is known as a system. A system can comprise of one or many subsystems, which is basically known as a system for us. So let us discuss about how do we represent the system mathematically. So we represent system mathematically by using the transfer function h of the system. So therefore, let us suppose there is a system which is going to have some input x of t and which is going to produce some output y of t. That system I can represent as simply y is equal to h of y of t is equal to h of x of t. Here in this slide, t has been removed here because I have represented this for discrete as well as for analog, discrete as well as for continuous signal. Therefore, I have intentionally removed that t part over there. So if you write y is equal to h of x, it is applicable to both continuous time signal as well as for discrete time signal for us. So here in this particular definition of a system definition, y is equal to h of x, where h denotes the operator known as a transformation symbol. So this operator is normally going to maps a function to a function, not a number to a number. What is the meaning of it now? X of t is basically a function. The x of t function is mapped to another function called y of t after modifying or after processing the signal x of t. So that particular response of a system is represented by simply h for us. Now the mathematical representation, another representation mathematical I can represent the system as x is normally going to produce y based on the properties of the system h, or I can say system h is normally going to produce a signal y. A system which is going to process the signal input x and produces y. So we have an operator called arrow operator. Okay, so this arrow operator is known as basically produces operator. So it says that a system h is going to produce output y when when it has been given with some input x. So equal to is something different here and this arrow mark is something different here. Arrow mark indicates that a system is going to process the input signal. So therefore I can say h is nothing but a system called as an entity. This entity is going to give a response y based on the input signal x. So therefore, I can just simply define a system based on this particular system here. X is going to produce y based on the operation of the system h. So therefore, I can also say another way of saying that the system h is going to produce system h is going to produce output y based on the input signal x. So equal to operator is something like assignment operator. That means whatever there on the right hand side will be assigning it to the left hand side. Whereas this greater than symbol operator, this arrow operator is going to indicate that the signal is simply going to get transferred from input to the output after processed by the system h. Now the system h is basically optional. We can simply avoid this particular system h. So this is the basic representation of a system x tends to y for a system h. So how do we read this particular statement here? X tends to y for a system h, or x system h is going to produce output y based on the input signal. So I can say that system is known as an entity which normally going to give a response to the input signal after processing is known as basically a system for us, basic definition. So that basic definition is simply applicable to this when once you put an arrow mark to this. So putting arrow mark, this is going to become the representation of a system mathematically. Okay. Now, basic definition already we have seen in the earlier classes. A system is an entity which responds to the input signal is known as a system. So often a system is defined by operator h and having the input x and output y represented in the form of a block diagram. Now, how do we represent a system in a block diagram? Input x will be there and this is a system h and this is going to be the output. Now usually the system h is going to be an ideal system which gives an ideal response when the input is going to be a impulse signal. So therefore, I can say this system H is going to be an impulse response system. So always in LTI systems, we consider system H is going to be an ideal LTI systems. What is ideal LTI system? Ideal LTI system is a system which is always going to give a response, valid response for a unit impulse signal. So if such a signal is normally used for our given input signal, what is output is going to produce? So it's going to produce an output which is going to be desirable output, because it has produced an output, it has produced a desired output when the input is an impulse signal. Therefore, the system is simply going to be called as impulse response system. So always we consider this H is going to be the impulse response system for a LTI system. Now in a quick while, we normally going to discuss what is the meaning of a LTI system, which is called a linear time invariant systems. Now systems can be connected in two ways. One is going to be series connection. That means system 1 and system 2 are connected in series, just like a battery in a torchlight, where we connect the batteries in a torchlight in series. So that is a series connection. And one more type of connection is going to be the parallel connection. Now, what is the difference between these two? These two connections now, the output of system in series connection, the output of system 1 is given as input to the system 2. Whereas in the case of parallel connection, both the signals are x of t as given as input to the systems which are connected in parallel. So we can have n number of such parallel systems, we can have n number of such a series systems. That means I can have H1, H2, H3, H4 in series, as well as I can have H1, H2, H3 in parallel like this. Okay, so you can have n number of subsystems here in order to form a system for us. So if it is the case with the series system, how we write the output response? Output response we can write as equal to y is equal to, so output we are going to take at the output of H2. So therefore H2 into, what is the input to H2? It's going to be H1. So H1, what is the input to H1? It's going to be X of t. So I've written it intentionally so that it is applicable both for continuous as well as discrete time systems. So for series connection, we can write the expression for the system response or a system as y is equal to H2 of H1 of X. Similarly, I can write it for parallel connection, where we are normally going to put an adder here. This adder is going to add the response of all these systems H1, H2, H3, so on up to Hn. And all of them are simply going to get added at the output. So the output is normally going to be the addition of the responses of all the subsystems connected in the parallel kind of a connection, parallel form of a connection. So this is known as a parallel connected system. So two types of systems we have in the syllabus: series connected systems and a parallel connected systems. Now let us move on to the another important topic, that is called linear time invariant systems. Now here we have two terms involved in this. One is linearity term is involved in linear time invariant system. We have a linearity term and we have a time invariance term. Now what is linearity? Linearity is normally going to support a superposition theorem. We already discussed in the very beginning chapters of the electrical technology about superposition theorem. Now same kind of a theorem we normally going to employ here, which is going to support both additive and homogeneity properties. Now, what is basically superposition theorem means? Let us suppose if you have more than one input to a system. Now, how do you find out output of a system? What we do is we individually apply the inputs and we find out the output for the individual signals. Then later on, we normally consider the output of a system with all the inputs after we apply the inputs collectively. That is what called basically superposition principle. Now in that it is going to support the homogeneity also. So what is, let us look into these two basic concepts, homogeneity and additivity. So linearity is going to support superposition theorem. Superposition theorem is going to follow two basic properties known as homogeneity property and additive property. What is homogeneity property? Homogeneity property is related to the scaling of the input signal. So output signal is always scaled by some constant alpha. That means, what is the meaning of scaling? Say for example, the system is going to process the input signal and it's going to provide some scaling effect. Say for example, if you are designing a attenuator is going to attenuate the input signal x1 of t. Say for example, if you give input x1 of t as 10 volts, output y1 of t will be getting as around say 5 volts. So that means there is a reduction of 5 volts. That is called attenuation. Now, if you apply the signal, that means if you apply the another signal of 20 volts, then proportionately that much change has to occur in the output signal. That means here, if you apply 10 volts, I am getting 2 volts. Means what? It is going to be 1 by 2. It has been divided, the input signal has been divided by 2. If you apply 20 volts, output should be 10 volts. If you apply 40 volts, output should be 20 volts. That means the scaling factor is always going to remain constant. If at all the scaling value is going to remain constant, it is known as, it is something like saying that the system is supporting the homogeneity. So attenuator is going to support the homogeneity property. So any system which is going to support this particular thing, scaling, the scaling value which is there at the input is going to be same at the output, then it is going to be homogeneity property. That is what one way of homogeneity. Another way is what, that say output is producing some predefined output. Now if the input to such system is alpha, same alpha has to come at the output. That is what called homogeneity. Okay, so that means it is all based on the application. We can just really implement or incorporate this homogeneity in the LTI systems. Now here, as far as the definition of homogeneity is concerned, whatever may be the scaling at the input, the same scaling will be coming as it is at the output. Say alpha is 2 by 5, same 2 by 5 will be coming here. If alpha is 1 by 5, 1 by 5 will be coming here. If alpha is 1 by 2, 1 by 2 will be simply coming over here. So that means the scaling value, whatever we normally going to have at the input, same scaling is going to get propagated to the output side of the signal. So if, for example, another signal, if I give alpha into x of t, it is going to produce alpha into y of t. So this property is simply known as a homogeneity property. The next important property is going to be additive property. What do you mean by additive property? Just now I was speaking about the superposition theorem. Say for example, E1 is the input, E1, E2 are the inputs. For E1, if R1 is the output, for E2, if R2 is the output, then the output y of t, when you add up these two outputs because of the individual inputs E1 and E2, is going to be say R1 and R2. Now next time what I'll do is I simply add E1 and E2 at the input, then I'm normally going to get the output as R1 plus R2 only. So the output what I got after I combine the two inputs at the input, and the output that I got from the individual inputs should be compulsorily same. If these two are going to be same, then we say that it is supporting a additive property, something like a superposition theorem. In superposition theorem, what we are going to do, in order to find out the output of a system for multiple inputs, what we do now, we apply one input and we find out the output for that corresponding input. Like that, for every input we find out the outputs for the corresponding inputs. So after we get all the outputs, then what we do now, we say that for this many inputs, if we add up all these inputs, the outputs is going to be simply sum of the individual inputs. So that property is simply known as a additive property. So therefore, how do we define the additive property now? Additive property is normally going to give a response of a system. If the response of a system is same for individual inputs and sum of the all inputs, then it is simply known as a additive property. So individual inputs output, when you add up, that should be same as the output which response which we get by summing up all the inputs. That is simply known as additive property. Now when you combine these two, when you combine the homogeneity, now I am simply multiplying alpha into something and I'm adding two inputs. Means what? I am incorporating additive property and homogeneity. Both of them are included in this particular type of a system. Now it is going to produce output y of t, which is going to be alpha of y1 of t plus alpha of y2 of t. So it is supporting both additive property as well as the homogeneity property. Because alpha, same multiplication factor, is propagated in the output y1 of t and y2 of t. Therefore, I say that it is supporting the homogeneity. And as the input is added here with plus sign, output is also going to get added by plus sign. So we say that this system is simply a linear time, a linear system. Now, right now I did not get into invariance. No, this system is known as a linear system. Now, To get a linear time invariant system, the system should be time invariant also. Then you have to combine linear property plus time invariance property of a system to get a linear time invariant system. So let us look into this property in a homogeneity with some values, with some values. So for example, there is a system h of t. As I was talking to you about h of t, what is h of t? H of t is known as a response, unit impulse response of a LTI system basically. That means what is the meaning of it? The system uh, whatever we normally going to put here for processing should be a impulse response system. So after we test the system with impulse response, if the impulse response is satisfactory, only that system we are going to use in our LTI system. So therefore, the linear system H of t is not known as a impulse response system for us, which is normally going to give a response in a time domain. If I write h of t, it is nothing but response represented in time domain. If I write H of omega, I am representing the signal in terms of the frequency domain. So therefore, let us look into this example now with some values. Now imagine that there is a system h of t, right, where the system is going to give a response for a given input. Now what is the response it has given? It has given the response 8 for a given input 20. Now for all this system, I am using a scaling value alpha is equal to 2 by 5. So alpha is 2 by 5, same alpha has to be propagated to the output. Now let us apply the another input now. I apply another input with input x of t is equal to 10 and y of t I will be getting as 4. Now when I add up this 10 plus 20, what is the output? 8 plus 4, that is going to be 12. So even if I add the two signals 10 plus 20, I should get output as 8 plus 12 only. I should not get anything else other than 8 plus 12. If I really got exactly as 8 plus 12, means what? The system is supporting the scaling as well as additiveness. That means it is supporting the homogeneity property as well as additive property. Therefore, we can call this system as a linear system. So this is how the linear system is normally going to behave. So therefore, practically, the linear systems are going to be much easier to design because they are known as the ideal systems. Okay. So than the non-linear systems. So linear systems are much easier to design than the ideal systems for us. So we prefer LTI systems in designing any system. Let us look into another concept, that is time invariance concept. What is time invariance? Basically, time variant and time invariant systems. In this, what is time variant? See here now, if E1 of t at some time period t is going to produce, this arrow is nothing but produce, is going to produce R1, then same signal at another time instance, some t plus t is applied, it should produce the same output R1. So that means since the output produced by the system is the same, irrespective of the instance of occurrence of the signal with respect to time, then the system is going to be time invariant. That means without depending on the time of occurrence of the signal, the system is normally going to give us a response. That is known as a time invariant system. It is something like switching on the light or switching on the fan. Whatever may be the time at which we normally going to switch on the fan or a light, we normally going to get light and a fan. The output is going to be same irrespective of the conditions of the weather. Irrespective of conditions of the weather, we will be getting the same output. The light is going to glow with the same luminous value. The fan is going to revolve at the same RPM. That means the response of the system is not going to change irrespective of the time period, time of occurrence of the signal. So that system is known as simply a time invariant systems. Okay. So let us look into the representation of a system now. I can represent the system as h of t, as I tell you already, and input is E1, output is going to produce R1 irrespective of the instance of occurrence of the time period. Now another system I have, Okay, so this is what the system which we have got now, which is going to be as output response R1 irrespective of the occurrence of the input. So E1 is occurring at t is equal to t. Here E1 is occurring at t is equal to t plus t. Even though the input is applied at different time periods, but the output response is going to be same, which is going to be R1. Let us look into the next. This particular thing is known as time invariant system. The output is totally independent of the input, independent of the occurrence of the time period of the signal. Therefore, it is called as time invariant system. Another type is going to be time variant system. That means based on the time of the based on the time of existence of the signal, the output should compulsorily come. It is called time invariant system. So, for example, if you design any automated system, what is the meaning of automated system? Based on the time, based on the weather conditions, the light should either glow more or should glow less. Then it becomes like a time invariant system for us. So the system is going to behave differently based on the time. Okay, that is what called time invariant system. So therefore, if I take system h of t as a system, as a impulse response, h of t is represented as the impulse response of LTI system. Then if E1 is the input, R1 is the output. Now, another condition, if E1 is going to exist at t is equal to t, it is going to produce another output as R2. Output is different. So, which is known as a linear time invariant systems. So, this is the system which we normally going to have, which is very, very important for us. So, these two are the very important systems for us for analyzing the systems for a given signals. Okay, so that's why the time invariant systems and time variant systems are going to be so important for us. Now, how do we form an LTI system now? In the previous slides, what we discussed about linearity, we discussed about the time invariance, okay, and time variance. Now, when you combine these two, we normally going to get a linear time invariant systems. So we can form an LTI system by simply combining the properties of linearity and time invariance. Okay. So why we normally going to deal with these LTI systems? Because in all engineering applications, LTI systems plays an important role. Why? Because it is going to be known as an ideal system. So always we have to compare our responses with the ideal system responses, and we should figure out how far we have reached, how efficient, how effectively we got the output based on the ideal systems. Therefore, LTI system plays very, very important role to analyze any practical real-time systems. So in practice, systems are not going to be LTI systems, but still we normally going to approximate that system by using with the LTI models to know about the perfection of the real-time systems in practice. So even when dealing with systems that are not LTI systems, we still use a LTI systems because they play an important role to analyze the system uh, system properties. Now, next types of systems are going to be, we have a casual system, we have a stable system, we have a shift invariant system. Okay, and the operations we normally perform on the signals by the system is going to be convolution property. So these concepts we discuss now. What is casual system? What is casual? Casual means what? Any system which is not normally going to produce output without bothering about the future inputs is known as a casual system. Okay, so that system is known as basically a casual system. So we can define the causal system by three means. There are ways on which we normally define the system. The definition is going to be same, but the way we represent the system is normally going to be different. So we can use these different definitions of a causal system on different contexts. Okay, let us look into this now. So if any system cannot anticipate the future values based on the present and previous input values is known as a casual system. A casual system is a system which won't anticipate the output response based on the present input and the present and the previous inputs of the signal is known as a causal system for us. Now we are dealing with the system actually. System response is represented by what? H of t for us. So if h of t is equal to 0 for all t less than 0, Means what? Our system response normally going to start from t is equal to 0 to t is equal to some instance of time period for us. Okay. So that means here before t is equal to 0 means what? It is going to be something like h of t is normally equal to 0 for all t less than 0. System does not respond to the input other than the present and the past inputs. So the present inputs is normally going to start with t is equal to 0. Sorry, past, present system is going to start its response from t is equal to 0, and it is going to start giving response for the inputs at t is equal to t1, at t is equal to t2, at t is equal to t3, so on. So for example, if you are stopping at t is equal to t4, then that system is going to give a response only for the inputs which are going to happen from t is equal to 0 to t is equal to t4. So if a system is has to respond, if a system could not respond for the input at t is equal to t5, then that system is simply going to be called as a casual system for us, because input is applied at whenever we apply the input at a particular instance of time, then only we normally going to know the output of that particular system. Without that, we cannot really predict or anticipate the output of a system for a future values of the input. So say for example, presently you are at T3 time period, the input is applied at T3 time period. Say you expect the system to give the output at T5 time period, which is not possible in the case of the casual system. So any system which supports that is known as a casual system for us. So the simplest way to define a casual system is you can define h of t. H of t is equal to 0 for all t less than 0. So is simply known as a casual system representation. In the exam for 2 marks, he'll ask us to define casual system or define casuality. So in that case, what you have to do now? Simply write down if any system say h of t is equal to 0 for all t less than 0, that system is simply known as a casual system for us. You need not write all these definitions and all whatever I gave you. It is all I gave you for explanation. If time permits, you can write them in the exam. Otherwise, this h of t is equal to 0 for all t less than 0, okay, for a system, then if a system is going to support this property, that system is known as a casual system. That point you can write in the exam for 2 marks. If it is given for 5 marks, then you have to write and elaborate all these things, whatever I am presenting in the PPT right now. Now, another definition I can give for system in terms of the say discrete time system. So in terms of discrete time system, what I can give now in terms of discrete time system now. Okay. So a system with input x and output y is said to be casual if for every integer n naught, y of n naught does not depend on x of n for some values, for all the values n greater than n naught. That means what is mean by the limit n greater than n naught? Future values of n. Future values of n. That means if n naught is the limit for the input presently, what is going to be n greater than n naught? They are known as future inputs. So y of n does not exist for all x of n whose values are going to be for n greater than n naught. Then that system is simply known as a casual system for us. Another definition I can give is R. If the output of a system, if the output of system at T naught depends only on the values of input for T less than or is equal to some T naught. So I was talking to you now. Now I have taken some time period, present time period as T naught. So until T less than or equal to T naught, the system is going to give the response. So if the system of if the output of a system at T naught depends only on the values of input for T less than or equal to T naught, so that the system if the output if the system is producing the output for all the values T less than or equal to T naught, then only that system is called as casual system. For all the outputs for the inputs greater than T naught, if it does not produce any output, then the system is known as a casual system for us. So casual systems are basically physically realizable systems, because always the user wants the output after he gives the input, and he expects the output to be proportional to the applied input. So future giving the output signal for a future values is something like a probabilistic system, which we normally use it in artificial intelligence applications. But basically, in ordinary systems, normal systems, all ordinary normal systems are going to be casual systems. Say, for example, transmitter, radio transmitter is a casual system. Radio receiver is a casual system. So all these are not casual. That means usually most of the systems are going to be casual systems. Therefore, these casual systems can be called as a physically realizable systems. We can able to implement these systems very easily in the real time. So that's why this is going to be very, very important type of the system which we have in the syllabus. And another system is going to have stability. So system is known as BIBO system. What is BIBO? It is called bounded input, bounded output system is known as a BIBO system. An LT system is called as BIBO stable if its impulse response is absolutely integrable. So already we discussed about the what is this integrability. Okay, we have discussed about the stability of a signal also. So if the signal is going to absolutely integrable, it is going to be called as a stable system. Similarly, system is going to be something like a signal which is stable. If the value of the signal is going to be absolutely integrable, then it is going to be a stable signal for us. Similar to a stable signal, we have a stable system, stability of a system. So for all the bounded inputs, if the system is going to produce the bounded outputs, then that system is normally going to support the stability. And hence I can say that system is a stable system. So any system which is going to be stable, which is always going to produce bounded outputs for the given bounded inputs, then that system is simply known as a stable system. So it is going to support the property called stability property of a system. So here one of such mathematical representation has been given for the stability of a system. So for example, h of t, see here, h of t is the impulse response of an LTI system. So for a given input, if the signal is absolute integrable, then if the system is absolute integrable, that means if the system is going to produce some finite value which is not going to be imaginary, then that system is going to be known as a stable system for us. So we can say that the stable systems are always going to give us a value, give us a finite value in the output. If any system is going to give us if any system is going to give us a finite value, a defined value, then we can say that that system is known as a stable system for us. And it is supporting the property called stability for us. And one more type of system we have, which is going to be called as memory-less system. What is memory-less system? The output of a system does not remember the previous inputs. If the output does not depend on the previous inputs, it is known as a memory-less system. Memory system is what? It remembers the past inputs. Okay, it's known as a memory system, obviously. So how can we define the memory-less system? I can write y is equal to k into x of t, where k is known as some transformation factor of the system. Where to get this output y of t, it does not depend on the previous values of x of t. So such system is simply known as the memory-less system. So and hence we can define the memory-less system as a system whose output depends only on the present values of the system, present values of the input signal x of t. Then that system is known as a what is this memoryless system? Okay. The next concept we have is shift invariance system. So already we discussed about this kind of a shift invariance kind of thing in the periodicity. What is that we discussed in periodicity? The shape of the signal or the form of the signal is normally going to become independent of the existence of the time period. So if t is the time period of the signal, let us take the signal existence at 2t, 3t, 4t, 5t, so on and so forth. The signal form should be same if it is going to be periodic in nature. Say for example, if we give a sine wave signal, the sine wave should be there as sine wave for all the different finite time instances capital T. Then if it is so, then I can say that that system is known as a periodic signal. If a signal is going to be a trapezoidal signal for all the time instances, then it is also known as a periodic signal for us. Similar to that, we normally going to have a shift invariant system. That means if at all there is a shift in the time domain, the system is going to experience same amount of shift in the time domain irrespective of the existence of the time, occurrence of the time. So when that shift in the time domain is going to come across in the input, it doesn't matter. Whenever, whichever may be the time instance where the shift is going to happen in the input signal, the same amount of shift you're going to find at the output signal. So the system is simply called as a shift invariance system. It is also kind of a time invariant system kind of a thing. So whatever may be the existence of time, irrespective of existence of time, it is going to give you the output. That means the output simply depends. What is this? Time invariance means what? Say the time is shifted, but the output is going to be same as in the case of time invariant system. This is shift invariant system. Invariant means what? There is a shift in the time, but same amount of shift you're going to find in the output. It's called time invariant system. What is LTA system? Even though you have a shift in the time, even though you have a shift in the time, but the time shift is not going to get seen in the output. So it becomes irrespective of the time shift. That is called time invariance. So time variance means what? Obviously it is going to be it's going to depend on the time. So shift invariance means what? There is a shift in the time domain. That means if at all there is a shift in the time domain, same shift you're going to find in the output. It is known as a time invariance system. So what? How can we define this time shift invariant system? So basically, this shift invariant system is normally used for discrete time systems. So a shift invariant system is the discrete equivalent of a time invariant system defined such that y of n, if y of n is the response of a system x of n, then y of n minus k is going to become the response of the system to x of n minus k. That means in a shift invariant system, the contemporaneous response of the output variable to a given input variable of the input variable does not depend on when the input occurs, on when the input occurs. So it only looks into the time shift. So when the time shift has occurred, it don't bother. Whatever may be the shift it is, the same amount of shift is going to get replicated back in the output. That is known as a shift invariant system. So in the case of discrete systems, how can we define that? If y of n is going to produce the discrete time output for a given discrete sequence x of n, then the response y of n minus n naught is going to be the response for an input x of n minus n naught. Then that type of system is known as a shift invariant system. So therefore I can define the shift invariant system also in another manner, is one where a shift in the independent variable of the input signal causes a corresponding shift in the output signal. So if the response of the input signal y x of n is y of n, then the response of the input to x of n minus n naught is also going to be y of n minus n naught. That means here we can say that a shift invariant system is one where a shift in the independent variable of input signal causes a corresponding shift in the output signal also. So that is known as a time invariant type of the system, for example. And next one is going to be the operations on the what operations the system is going to perform on the signal. One of the operation is going to be the convolution operation. Convolution in a simple sense is simply called as a multiplication kind of thing, but not truly sense perfect multiplication. So in a scalar, if you say 3 into 2, it's going to be 6. So that means 3 is multiplied with 2. That is some operation we are doing called multiplication. So similar kind of thing we normally going to do for the signals. If two signals are multiplied, then that is simply called as a convolution for us in general. So convolution is related to the vector product of the two signals. So I can define convolution as simply vector product of the two signals. So the output of a system for a given input is represented by the convolution integral. So one of the operation, very important, one of the important operation that a system will do on a signal is going to be the convolution operation. That means the response of the system, the response of the linear LTI system on the input signal x of t, okay, is known as a convolution for us. So how we can define this as something like y of t is equal to integral of x of tau h of t minus tau d tau. What is this I am doing here? I am simply multiplying the response of the system with the input signal. Now here to multiply this, how I am simply multiplying? I am time shifting the response of the system, and I am multiplying the system response with the signal value at that particular instance called a tau, where t is going to be the time of instance, tau is going to be dummy variable which we normally going to shift, right? That means here something like we are normally going to scan the output y of t at various instances of t minus tau in a continuous time signal domain. So now here, what kind of signals are suitable to involve in the convolution process? There is some mathematical analogy here, simple analogy. Any system, any signal cannot be suitable, is not suitable to apply convolution property. So now, what kind of signals are suitable to apply this convolution property? Let us look into this. Since any sinusoidal signal can be represented as continuous integral of weighted impulses, now, any sinusoidal signal that can be represented as a continuous integral of weighted impulses, only that kind of signals are suitable for the operation called convolution. Which means what? If you multiply simply the weighted impulses with the signal x of t, then it should compulsorily produce the signal x of t at that instance of time period. Okay. So when you do it continuously over the interval minus infinity to plus infinity, now I can say here, see this waveform now. I have just shown you some waveform here. There is a sinusoidal variation signal here, and the signal is simply sampled. See these samples now. Now the sampling interval is delta. Now how can you say that when delta is normally tends to zero? When delta is normally tending to zero, means what? You normally going to get a very smooth response curve. We normally going to get a impulse values. That means this delta value, if this becomes equal to zero, it is known as the impulse signal. What is impulse? Impulse signal is a signal which is going to exist only at an instance of time. Other than that, the impulse is not going to present as far as that instance is considered for us. So therefore, when such an impulse signal delta is multiplied with the input signal, now we normally going to get that signal at that particular instance of time. That means it's something like 1 into x of t is equal to x of t. This delta of t minus t, this delta function, I can represent by 1 in a scalar notation into x of t. I'll be getting x of t. That means whatever may be the value of signal that will be there at an instance of instance of tau, that signal we normally going to get at the input. So if you remove this integral, what I can write this as x of tau is equal to delta of t minus tau into x of tau. If you put integration, means what? I will be tracing the complete signal from these individual samples, where the sampling interval, see the sampling interval delta, it becomes equal to 0. As it tends to 0, as delta tends to 0, we normally going to get a perfect convolution of the signal. Now the signal, this particular signal is simply multiplied, this value of signal x of t is multiplied with the system response, is multiplied with system response at every instance of tau. Then we normally going to say that we have got a convolution of the signal. That means signal response of a system is normally going to get represented as y of t. That response y of t I can write as equal to x of t into h of t. It is something like a convolution operation which we can normally define here. So convolution can be defined as simply equal to x of integral of x of t, x of tau into h of t minus tau d tau, where the integration is going to ranging between minus infinity to plus infinity. What is minus infinity plus infinity? See, this signal is ranging from this value is, imagine that it is minus infinity, it is going to be plus infinity if you're going to consider from this value. Or otherwise, if you're considering the sample values from this location, we say this is minus infinity and extending up to plus infinity. So like that, for a continuous signal, we can represent the entire continuous signal response using y of t is equal to integral. As I was talking to you, integration is used for continuous signal representation, whereas summation symbol is used for the discrete time signal representation for us. So therefore here I am writing the response of the system, okay, whose response is nothing but the operation called as convolution operation. That means the system is normally, this LTI system is giving a response y of t. after after the signal is been after the x of t is been processed. Now what is the process it is doing? Convolution process or multiplication process. So after multiplying the there are some drawbacks. So at last, what the system is doing, the system is actually doing the process called convolution. So in this convolution, what is exactly happening? What is exactly happening here? In convolution, the signal x of t is simply getting multiplied with the impulse response of the system under consideration. So here in this process called convolution, what exactly the things are happening now? We are simply getting the area, effective area after multiplication of the signal with the transfer characteristics of the function under consideration. So in this process, say this x of t is fixed now, whereas x of t minus tau, tau is taking different values. If x of t is fixed, this h of t minus tau is nothing but the transfer function of a system, and this function transfer function is taken, and this function is normally used to scan the x of t. Something like imagine that I have a system function like this, like a rectangle I have. This h of t minus tau is a rectangle. This rectangle function I am normally going to scan on this x of t. Imagine this signal, whatever that we have after impulses, is nothing but a signal for us, x of tau. Now we scan the x of tau with the impulse response of the function h of t minus 2. We scan like this on this. So the resultant of scanning is what? Multiplication of these two. Now all these values are going to happen, are going to happen for all delta tends to 0. If delta tends to 0, we normally going to get the impulse response. So by that, what we get now? We get the overall response of the system y of t. So we can normally say that the system is normally going to give us a convolution integral for us. So this integral is known as a convolution integral of the system, right? So now here what is important is that one more point which is important is whichever signal we use in the process of convolution, compulsorily that signal should satisfy the shifting property in the signals and systems. There is a concept called shifting property. Any signal which satisfies the shifting property is normally used, or it is suitable for convolution process in the convolution integral. Okay. So any system which is going to perform, any system which is going to involve in the convolution process should satisfy the shifting property. What is shifting property? We can normally say if you take this t is replaced with tau and remove integration, at every instance of tau, we normally going to get a signal at that particular instance. That means, say for example, imagine this is tau. Imagine this instance is going to be tau. Now at t is equal to tau, delta of t minus tau, this impulse, imagine that is an impulse signal. So this impulse signal, the delta of t minus tau is multiplied with this signal. Now this is a signal x of t. This signal is multiplied, now you normally going to get the value here. Something like 1 into x of t is going to be that x of t value over there. So we will be getting the value at tau. So since if you apply, when you apply the unit impulse response at t is equal to tau, that means at delta of t minus tau, if you apply impulse response, then we normally going to get the value of the signal at that particular instance of time at x of tau. So x of tau becomes equal to, if you remove the integration part, x of tau I can write as equal to delta of t minus tau into x of tau. We normally going to get x of tau only. So which means what now? It is supporting the shifting property. So any signal which supports the shifting property is normally suitable to use in the process of convolution. So that is what we have to remember in the mind whenever we normally going to use a signal in the convolution process. Now another important point is that when you can go for convolution, we can go for convolution under the limitation that this delta, the sampling interval, the difference between the two samples, when it becomes equal to 0, means what? we normally going to get a impulse response, and that impulse response here we are going to use as h of t minus tau, and that is used in the multiplication process with the signal to get the overall output signal. So this is how we normally perform in the process called convolution, and this integration is known as a convolution. This integration is known as a convolution integration equation for us. Well, so the response of a linear system for an arbitrary input signal x of t, for arbitrary input signal x of t, can be given by the convolution integral as given below. Okay, so this is whatever we have just explained just now. I can write the convolution integral as y of t is equal to integral of integral of x of t into h of t minus tau d tau over the limits minus infinity plus infinity. This is known as a convolution integral. So finally, what I can say that the above equation indicates that the continuous time LTI system is completely characterized by its impulse response h of t. So the entire convolution process is normally characterized by the impulse response of the LTI system. So the system h of t that we use should be an impulse response of a LTI system. So the convolution process is entirely characterized by the impulse response of the LTI system. Now mathematically we can say convolution as by the symbol as star, by the symbol called star. By the symbol called star we can use the convolution integral. By the symbol called convolution integral we can use the star operator. So the above equation also defines a mathematical operation between the two signals called as convolution signal and is denoted by star, and can be written as something like x of t star h of t is equal to y of t, which is known as, this star is known as a convolution symbol, which indicates that the two signals are simply multiplied in the vector domain. That means it is going to be a signal multiplication, is known as a convolution. So it is simply convolution of a signal represented by star operator. X of t convoluted with h of t is equal to known as y of t for us, because h of t is equal to what? Y of t by x of t. Therefore h of t is equal to y of t by x of t. So x of t into h of t is equal to y of t. General relationship we have. I can write this as a convolution integral. In the next class, what we do is we'll discuss about convolution sum. So convolution sum is normally applied for what type of systems? We normally apply it for a discrete systems. For a continuous signals, we normally perform convolution integral. For discrete signals, we normally apply the convolution sum. So more or less what we can say is convolution is something like getting the or finding the multiplication of two signals. If it is in the time domain, we go with the convolution integral. If it is in the discrete time domain, if it is in a continuous time domain, we go with a convolution integral. If it is with a discrete time domain, then we go with a convolution sum. So now this is nothing but a system representation. So whenever system representation is involved, what is so important is that you should compulsorily involve the message signal, the input signal, the transfer function, that is the system function, and the output function y of t. Okay, so that means here using this particular convolution notation, we are representing the output signal y of t or output function y of t in terms of the convolution integral. Okay, now x of tau is a function. All right, so y of t is a function. Now, because of the process called convolution, we normally going to get a response. Okay, now the response we get y of t depends on the impulse response of the system under consideration. Okay, so this is what altogether the convolution integration process. In the next class we deal with the convolution sum. So therefore we apply convolution sum for the discrete time systems. Thank you very much for today's session.